Okay, so this is a continuation of the pulley ramp question. So I just tidied things up here. I said, okay, originally to come up with the acceleration of the system, let's think of the system as a whole. So we sort of do this blobby thing and said, well, what forces are causing this to move? Okay, it's going to move all together. So this end of it is going to be moving down or up vertically, and this end of it is going to be moving up or down the ramp. So let's just look at the forces that either pull it up or down the ramp or up or down here. So we've got gravity pulling us down, 490 newtons. We had the x component of this guy's gravity pulling us down when we made our x and y. Ugh, that's really messy. When we made x and y along the ramp or perpendicular to the ramp. Okay, so x was down the ramp, so we got 392 newtons, and then we said, okay, let's figure out the net force. So I think it's going to move this way, so we labeled this the driving force, minus this is going to be the retarding force because it's acting against our motion. Driving minus retarding, total is 98 newtons. Okay, that's the net force acting on the system. Now, the net force is equal to the mass of the system times its acceleration. The mass of the system is the combined masses of the objects inside the loop, in the system. So 80 plus 50, that works out to be 130A. Now, this is the net force. This is what the net force has to be equal to, m times a, from Newton's second law. So 130A equals 98, A equals 98 over 130, or if you pull out a calculator, this is what you get right here. Okay, so I'm going to write this number up here, A equals 0.754, because we're going to use it for the second part of the question, meters per second squared. Okay, so now we can get rid of this whole part here. Okay, and I'll just write this mass back in. This is a 50 kilogram object. And this is great. We've broken the system open, which is exactly what we need to do to calculate the tension in the rope, because the tension is in here. And if it's all contained inside the system, we don't really know what's going on there. So what we're going to do is bring out a pair of imaginary scissors. These are my scissors. And I'm going to cut this rope right there. So now I'm going to have this situation like this. Okay. Everything is the same as before. This is a free body diagram, so I may be cutting it here, but there is tension acting in an upwards direction. And that's what I'm interested in. What is that tension? There is gravity, same as before, mg, acting in the downwards direction. Okay, I know this whole system is moving downwards. That means this part of the system is also moving downwards, which means that the net force acting on it must be downwards. Now, the net force acting on this particular part of the system is equal to its mass times its acceleration. So it's a 50 kilogram object, but the whole system, of which this is part, is accelerating at this rate. So this is the acceleration of this part of the system, as well as of the whole system. So 50 times that. So bring up my calculator. I still have a little more precision here too. So we're going to go, that's the acceleration times 50. And that comes out to be, let's call it 37.7. Okay, great. So this is equal to 37.7 newtons. Okay, so we actually already know the net force. which is great because one of the forces on our free body diagram is missing, namely the tension. Okay, so mg is equal to 490. So the sum of the forces in the diagram here must be equal to the net force. So T, it's going to be an upwards force, minus 490. So now I'm replacing vectors with signed numbers. So I'm saying down is negative, up is positive. So T minus 490 is going to be equal to, this is also a downwards force, so minus 37.7 newtons. So to solve for T, I'm going to add 490 plus 490, and I come out with the tension is equal to 490 minus 37.7. That's going to be 452.3 newtons. Okay. So the tension is almost equal to the downward pull of gravity, just a little bit short of it, which gives me a net downwards force of, oh sorry, that should say 52, a net downwards force of 37.7 newtons, which will give me exactly the acceleration that I predicted.